Now we are going to use truss elements to solve a problem. Our problem is a lantern support. There is a 20 kilogram weight hanging from one end of the support. Each member of the support are made of tubes with a square cross section. These are the dimensions, and they are made of structural steel with Young's modulus of 200 gigapascal. Short members are half a meter long. Okay, so now let's move to Ansys and see how we can model this structure. First, we need to create a new project. We have done it. Then we need to create a new static structure. We are dealing with a structure under static conditions or quasi-static conditions. Okay, we check the engineering data. We have a structure still selected already for us, and its Young's modulus is 200 gigapascal. So this is good. So we can continue. We don't need to define a new material. Next, we need to define the geometry. So we need to go to design modeler. Essentially, by defining the geometry, we are defining the lengths of the truss members as well as their cross-sectional area, and this is the information that we need to put into the element stiffness matrix. In addition to that, we need the Young's modulus, and if we have all this information, then we can formulate the element stiffness matrix and then assemble them to find the structure stiffness matrix. Okay, so we have the normal view to plane XY. And under sketching, we can use grid to guide us through the sketching. So here I make this spacing 0.5 meters just to help us for our structure. And then I choose line from here. You can see here the coordinates. So I start from 0, 0 to 0, 0.5. Next line from 0, 0.5 to 0.5, 0.5, and next line just linking these two ends. So we've got our structure, the sketch. We can dimension it if you like. I'm just showing one of those, so the dimension is 0.5. You can change its dimension if you need to modify this sketch. But essentially, this sketch is defining the path of the center line of different truss members. So next, we need to go to modeling, and we need to choose the sketch and go to concept and create lines from sketch. Okay, apply. This is done. And one more step is clicking generate, which then creates this body for us. So this is a body made of our sketch. As I said, we need to define the cross section. So our cross section is rectangular tube, and the dimensions are given, which are not the dimensions that we need. So I'm changing these to match the dimensions of our cross section. So you can see that in the window, when I'm changing these dimensions, the shape is changing, and this one is 0.02, so 20 millimeters edges. Okay, this is done. So next we need to assign this cross section to these lines, and this cross section essentially runs hits these lines at its centroid. So this path is defining the centroid of the cross section. Okay, this is done. So we can now go back to the workbench, and now we need to open the model. So what happens is that now the model will load the geometry, and we can do the rest, like assigning the material properties to that sketch, then meshing the sketch. So we create the actual elements, the truss elements, and then we apply boundary conditions. So the boundary conditions here will populate the vector of nodal displacements, the known elements, and then we apply force or forces, which define the vector of nodal forces. Okay, so in the display, I choose front view, One thing we need to do here on geometry, we need to change this from beam to truss. This is how Ansys would define a truss, define a structure made of truss elements. Okay, you need to do this step first. The material is defined, cross section is defined. Now we need to mesh it with truss elements. So in order to mesh it, I'm going to select the sides or the members. I'm holding down Control, and once you have done that, you click Apply. You see that each side has been discretized with several truss elements. We don't want that. We want to have one truss elements on each side. So we choose this option, and number of divisions 1. Now we have one truss element on each side. So essentially our model is meshed now. Now I need to apply the boundary conditions. Okay. So the boundary conditions that I'm going to apply, one is simply supported on the top one. You can also use fixed. Both should give you the same results because you're using truss elements and they don't have any rotational degrees of freedom. They only have translational degrees of freedom. We don't have roller support here, so that's why I'm choosing displacement for that one. So for this node, I'm going to make the displacement fixed or 0 in X and Z direction, and it is free to move in Y direction. Hence, we are modeling a roller support. And now I'm going to apply the force here at this end. So instead of vector, I go for components, and I choose the Y component. I define it minus 200, so essentially 20 times 10. You should time it by 9.81, but I'm just making it simpler. And there you go. So it's been applied. We can now solve the problem. So here's the solution. So when you're solving it, essentially it's now taking all the information you have provided, forms the element stiffness matrix, the structure stiffness matrix, populates the elements of the nodal forces and nodal displacements that are known, and then solves for the unknown nodal displacements. Once you have that, then you need to do some manipulations to find the quantities of interest. For us, displacement is interesting. Beam results, we can look at axial force. We can look at a few other things like bending moment, and we can look at shear force. Okay, now we need to evaluate this. So it's using that information to evaluate these results. So look at this. This is displacement. You can see that members are free to rotate where they're pinned. This is correct. They are not bending. Great. This shows that these are truss structures. You can see the axial force in the members. I can use the probe function here just to see how much they are. So this is plus 200 newtons. So it means this member is under tension. This member is under tension. This member is under compression. Bending moment has to be 0 because this is a truss. In trusses, you don't have bending moment. Neither do you have any shear forces. So I hope this makes sense. This is a good start into using finite element modeling, and now you have learned how to use truss elements in Ansys to analyze a truss structure.